In this lecture, we will quickly recap the fundamentals of Docker. So here's a definition of Docker. And really, the key thing to understand is that the rise of containers is one of the most important trends in technology today, and Docker is essentially synonymous with containerization. Using Docker, you can quickly deploy and scale applications into any environment and know that your code will run. If the definition on the previous slide made sense, feel free to skip ahead. However, if you're still a bit unsure about what Docker is, you're not alone. When I first started as a developer, it took me a while to get the hang of Docker, and many experienced data scientists have confessed to me that they actually don't fully understand Docker. To comprehend what Docker is, it's easier to start with a metaphor than a technical explanation. And the Docker metaphor is a powerful one. Historically, a docker was a laborer who moved commercial goods into and out of ships when they docked at ports. There were boxes and items of differing sizes and shapes, and experienced dockers were able to load those onto ships in cost-effective ways. Of course, this whole system was overhauled when standardized metallic containers were introduced to put on ships. These could be loaded onto ships using cranes much faster than any human docker. In the same way, the Docker open source project provides a way of automating the deployment of applications as portable, self-sufficient containers. The concepts of container and image are probably the most important concepts in Docker, so it's worth spending a bit of time to make sure the difference is clear. In short, containers are running systems defined by images. These images are made up of one or more layers, plus some metadata for Docker. If you're familiar with object-oriented principles, another way to look at images and containers is to view images as classes and containers as objects. In the same way that objects are concrete instantiations of classes, containers are instantiations of images. You can create multiple containers from a single image, and they are all isolated from one another in the same way objects are. Whatever you change in the object, it won't affect the class definition. They are fundamentally different things. It's worth spending a bit of time considering the differences between Docker and virtual machines or VMs. Containers and VMs are similar in their goals, namely to isolate an application and its dependencies into a self-contained unit that can run anywhere. However, a VM is essentially an emulation of a real computer that executes programs like a real computer. VMs run on top of a physical machine using a hypervisor. A hypervisor, in turn, runs on either a host machine or on bare metal. Don't worry if this terminology is unfamiliar. The key thing to understand is that there are practical differences between the two. For those interested in learning more, further details can be found in the lecture notes. One key difference between containers and VMs is that containers share the host system's kernel with other containers. This means that Docker containers are very lightweight and fast, and since containers are just sandbox environments running on the kernel, they take up fewer resources. This means that you can create and run a Docker container in seconds, compared to VMs which might take much longer because they have to boot up a full virtual operating system every time. Okay, let's zoom in from the abstract to a concrete example. On this slide, you can see an example Dockerfile for a Python Flask application. If you're not familiar with Flask, don't worry, there are lots of links in the lecture notes, but for the purposes of this example, it doesn't matter. What the Dockerfile is doing is acting as a recipe for creating a Docker image. Each step builds upon the last in layers. And you can see here that at the top line, we specify a base image to build on top of. So it's Python 3.7 using Alpine Linux. We then specify a working directory from which our commands will be run. Then we set environment variables that are required by Flask. We install various dependencies. You can see how a requirements.txt file is copied over from our local machine. And then after copying the current directory from our local machine, we run Flask. We use the docker build command to create this image, and the docker run command to start the container, which is based on the image we've built. Now we will review these basic commands in the hands-on exercises towards the end of this section. Another area to consider is that there are thousands of Docker images waiting to be used. The default storage repository for these images is Docker Hub. This is an easy way to share Docker images, and we'll be making use of it in this course, including in the upcoming hands-on exercises. In the lecture notes, we will provide a few sample images to check out on Docker Hub if you would like to explore further. Okay, that's just a quick recap. More of this will become clear as we move into the hands-on exercises towards the end of the section, but do make sure you do that and review anything that you're not familiar with. Be sure to check the lecture notes because we will be using Docker extensively throughout this course. Okay, I'll see you in the next lecture.